The notion of connectedness for metric spaces is a bit more technical than the corresponding notion for the real numbers, but at the same time there's a lot of visual element to it, which we will discuss at length when we come to path connectedness. So let's just define the notion of connectedness, which is exactly the same as what we have already seen for metric spaces, for real numbers. Definition: let X be a metric space. We say X is connected if it cannot be written as the union of two subsets A comma B of X satisfying number one, A is not the empty set, B is not the empty set. 2, A closure intersect B equal to B closure intersect A is empty. Okay, so a set is said to be connected if you cannot write it as the union of two pieces that are not just disjoint but in a sense essentially disjoint. That's what this A closure intersect B and B closure intersect A equal to empty saying. Of course, neither of these sets should be empty. Now two non-empty sets, subsets A comma B of X are said to be separated if A intersection B closure equal to A closure intersect B equal to empty set. In other words, if you can write X as the union of separated sets, then we say X is not connected. Okay, so if X equal to A union B with A and B separated, we say X equal to A union B is a separation. Okay, in this event we also say X is disconnected. So the definition is exactly the same. Let me make a remark that will be utterly trivial to prove. Remark: if A union B is a separation of X, then A and B are simultaneously open and closed. I want you to check this. It will take only a minute or two to check this. Whenever you have a separation, both these sets are actually going to be both open and closed. Another remark, if S subset of X if S is just a subset, then we say S is connected or disconnected if S considered as a subspace, so we treat S as a metric space in its own right, is connected or disconnected. That is sort of the obvious way to formulate connectedness for subsets of a metric space. Now note that the definition of connectedness did not actually involve the notion of the metric. All it said was A closure intersect B and A intersection B closure should be empty, and we have seen closed sets can be defined entirely in terms of open sets. Closed sets are the duals of open sets, that is, a set is closed if and only if its complement is open. So we don't have to go to the notion of metric to decide whether a set is closed or not. We can just do it by considering the topology. So all this is leading to the final remark, which is actually quite important. Connectedness is a topological property. Connectedness is a topological property. What this means is that if you choose a metric space XD and choose another metric D prime that is actually equivalent to D in the sense that both D and D prime generate the same topologies, then XD is connected if and only if XD prime is connected. So connectedness is a topological property, and it is some notion that does not depend on the choice of metric but only on the topology that the metric generates. So the moment we have a complicated notion like connectedness, we should try to characterize it in multiple ways so that we understand it completely. So notions of connectedness. So I'm going to prove several statements are actually equivalent. So let X be a metric space. Let X be a metric space, then the following are all equivalent. Number 1, X is connected. Number 2, the only subsets of X that are both closed and open are the empty set and X itself. Number 3, any continuous function f from X to 0 1, of course you give 0 1 the discrete metric, is constant. I'm not even going to bother writing down what the metric on 0 1 is. In fact, there is only one metric possible on 0 1. I mean, essentially you can put many metrics, but all of them are essentially going to be the same as the discrete metric. Okay, so any continuous function f from X to 0 1 is going to be constant. Again, the proof of this is rather straightforward, so let's begin by showing that 1 implies 2. Okay, now suppose 1 is true, that means if X is connected, so suppose S is open and closed. Then of course X is S union S complement, and S complement is open and closed, because open and closeness are dual notions of each other. So if you start with a closed and open set, then its complement is also closed and open. But because S and S complement are both open and closed, S closure intersect S complement equal to S complement closure intersect S, which are both empty. Which means if S and S complement are empty or non-empty, then X cannot be connected. This will form a separation. So we are forced to conclude that either S is X or S is the empty set, which is what we had claimed. Okay. Now coming to 2 implies 3. So we assume that the only closed and open sets are those are the whole set X and the empty set. Let f from X to 0 1 be continuous. Then f inverse 0 and f inverse 1, the pre-images, are both open and closed. This is because this singleton set 0 and singleton set 1 are both open and closed subsets, because we are putting the discrete metric on the codomain. inverse images of closed sets are closed, inverse images of open sets are open under continuous mappings, are both open and closed. Okay, but you cannot, I mean the only possibility is that that means f inverse 0 must be x or empty, and f inverse 1 must be x or empty, because the only closed and open subsets are the empty set and the whole set. This shows f is constant. This shows f is constant. Okay. Now 3 implies 1 is also equally easy. 3 implies 1. Okay. What we are going to do is, suppose A union B is a separation of x. Now we are going to define a function f of x is equal to 1 if x is in A. I put the flower brackets the other way around. Is 1 if x is in A, 0 if x is in B. Okay. Then f is obviously continuous. Check that. Here it might be useful to use the sequential criteria, or you can just take inverse images, it doesn't matter. You will be easily able to show that f is continuous. But that means f is constant. This shows A union B could not have been a separation. Okay. So what we have shown is the notion of connectedness can be characterized in multiple ways. Now it is advisable to use that formulation which is most apt for the scenario. We will illustrate this with a few theorems about connectedness. Theorem union of pairwise intersecting connected sets is connected. Intersecting connected sets is connected. So the setup is as follows. Let Si be connected subsets of a given metric space X. Okay. So take connected subsets of a given metric space X. Suppose Si intersect Sj is non-empty for all I comma j. Okay. Here the indexing set I, it might indicate that it's the integers, but nothing like that. It could be any indexing set. You could take any collection. It could be uncountable. It really doesn't matter. Then the union over I, Si is also connected. Now there are several ways to prove this. I am going to choose the way using the the continuous function characterization of connectedness. So let's call this set S, this union, let's call this S. Suppose f from S to 0, 1 is a continuous function. The goal is to show that this function has to be constant. Okay. Now because f from S to 0, 1 is continuous, f restricted to each Si is also continuous. Please check this. This is rather easy to do, but I'm going to leave it to you as an exercise. The restriction of f to each Si is also continuous. But this just means f restricted to Si is constant, simply because each Si is connected. Okay. Now Si intersect Sj is non-empty, and f restricted to Si is constant, and f restricted to Sj are both constant. are both constant, which just means f restricted to Si is equal to f restricted to Sj. Putting all this together, you just get f is constant. Okay, so that was rather easy. So I'll prove another theorem which is along the same lines. I will try to prove as much as possible using the continuous version of connectedness. I urge you that you should try to prove it with these, and in each scenario find out which is the easiest way to prove it. Let X be a metric space. Let X be a metric space, and let A subset of X be connected. Then if A is subset of B is subset of a closure, that means take any set that lies in between A and a closure, then any if A B is connected. So any set that is sandwiched in between a connected set and its closure is automatically connected. Again, here also the continuous version of connectedness, the formulation in terms of continuous functions is very useful. So suppose f from b to 0 1 is continuous. Suppose you take such a continuous function. Okay, then f restricted to A is of course constant. F restricted to A is constant, which means f is constant as well. F is constant as well because any point of B is adherent to A. This remark is not as cryptic as it looks like. F restricted to A is constant. Take any point in B, then there is a sequence in A that converges to B, converges to this point in B. Therefore, the value at this point is also got to be the same value as the value of f, which is just going to be constant, either 0 or 1. Okay, so it's trivial to see that any set that is squeezed in between a connected set and its closure must be connected. Finally, this is the behavior of continuous functions under connectedness. If X is a connected metric space, and Y is any metric space, and f from X to Y is continuous, then f of X is connected. So the continuous mappings take connected sets to connected sets. This is actually rather immediate proof. Let G from the image f of X to 0 1 be continuous. Then G circle F is constant. Because f is continuous, G circle F is continuous. So G circle F is a continuous mapping from a connected metric space to 0 1, therefore it must be constant. It is immediate that G is constant from this. Immediate that G is constant. So all of the results we have shown using the characterization of connectedness in terms of continuous functions to 0 1. Think about how to prove these three theorems using the other characterizations of continuity, and come to your own, other characterization of connectedness, and come to the conclusion of which method is the best for the given scenario. Okay, so this concludes this portion. We will now go on to path connectedness and connected components in the subsequent videos. This is a course on real analysis, and you have just watched the video on connectedness.